Good morning, everyone.
Good morning. How are you?
All right. Steven, I got your chapter 9 stuff finished yesterday or the day before, and just finished your chapter 9, your chapter 10 late last night. So I did get that worked on, and actually I ended up fixing everybody's because it seemed that I'd set it up in one version of mastering, but not in another. So, Steven, I did get your two homework sets fixed.
Uh, Professor Younger, did you get my email?
Thank you.
Who's this? Michael?
Miguel.
Miguel, sorry. Uh, yes, I remember seeing it. Let me double check what it was about while I'm waiting for everybody to log in. I got that. Somebody drawing. Yeah, I did. I did get yours. And let me double check. I think I even read it because it's already been marked through. Gotcha. That's yeah, that's a boo boo. So yeah, that'll be changed immediately.
Okay. Because I just finished it yesterday, and of course, because it was considered late, I got
Right.
no points on it.
Okay, gotcha. Yeah, so there was some 11:59 a.m. Assignments as opposed to p.m. assignments. So that was due dates. So that was a boo boo. I will fix that for those of you who've gotten weird grades already. I'll correct that as well. I think it actually corrects them by itself, so that's kind of nice. So yeah, thank you for letting me know, Miguel. I'm sorry I didn't. I evidently opened it but didn't read it. I think I remember what happened. Often when I open my emails, a lot of other things happen, and I get like
Yeah.
literally sidetracked right in the middle of an email.
Yeah, I
Sorry,
got you.
Miguel.
It's all right.
It's been
But
exciting
yeah,
having 45 students in a physics 241 class.
yeah, I can imagine.
I haven't had that kind of number since I was back at Chapel Hill, and that was like the small classes at Chapel Hill. But I had grad students that graded for me back then. That was nice.
41 was considered small back then?
Yeah,
Oh
yeah.
my
Our
God.
major classroom for like our calculus-based physics, which is really we offered the algebra-based, but our most students already had that when they came in. But our main room that we taught the 241 and 242 equivalent sequences, they called it math 24 and 25, I think is what it was. That was a room that sat 500 students.
I could never study with 500 other students. Oh my God. I
It
could
was
just
kind
not
of cool. It was
imagine.
like a stage or something. Like it had, basically it was round and it had all the seats set up. So like the top seats were probably 20 feet higher than the bottom seats. And then I had a bank in the front of six chalkboards. See, and actually it was more than six, but basically you had three on the right, and when you filled one up, you threw it to the top. Then you filled the second one up, you threw it just to the next to the top, and then you filled the third one up. Then you went to the next one next to that. So you could literally fill up six boards without having to erase. It was awesome.
Oh wow.
Other
I
than
feel like you
that, I
need a
mean,
microphone.
obviously as a student, you'd feel kind of lost, but the way they did it there, which snacks don't allow us to do it, uh, in the way that's necessary to do it at TCC, because I've actually had this before at community colleges and they just don't show up. But the way we did it at Chapel Hill is we had 3 hours of lecture, 3 hours of lab, but we also had 2 hours a week of what they call recitation. And it was completely optional, but basically what would happen, we'd have a couple grad students every now and then the professor would fill in too, where we'd come in and just solve problems for people, help them out, ask questions and stuff like that. But we get, out of a class of 500, we probably get, 50 to 100 show up. But it was completely optional, so they didn't have to. That's we actually tried that at COA, and they basically no one showed up. And I tried it at TCC once, and I think I had one out of 30 students show up, and then the following week I had zero. So I was like, oh well.
Yeah.
So yeah, they do the same thing in a lot of their courses, not just physics. I've noticed they did that at UC Berkeley with their Western Civilization course, which I really enjoyed taking through their internet. I actually contacted the instructor, and they gave me access to. They basically wrote their own Blackboard type software. They call it B Space, their own software department or their own department of programming wrote their own software, and they gave me access to the software, so I could actually literally like take the course. I just didn't get credit for it, so I got all the instructors' tests and downloads and all that cool stuff. But
That's
they
pretty
did the
cool.
same thing. They'd have like a 3-hour once a week recitation session where you work with grad students to get help.
Hmm. I feel like for a class of 500, like either the student or the teacher would need like a microphone to speak through.
Yeah, they a lot of them did. I could project my voice pretty well, and plus the auditorium type classroom that it was actually very beneficial to allowing music, I mean sound to propagate like that. If you look at those open courseware MIT courses, you'll see that's the same thing they're doing. Sometimes an instructor will use a little microphone, sometimes they won't. But yeah, it definitely helps to have a microphone, especially if someone's got hearing problems. Of course, we also had someone doing sign language right at the side of the class because there's always at least one person that needed sign language or something like that. There's always one or two people in there taking notes for other people because students had disabilities. Well, it looks like we got 28 out of the 45. This is starting to worry me. I don't know how many people have dropped, but anyways, we had 45 people enrolled. I think the last I checked, we still had 40 enrolled, and we're looking at 28 participants today, and one of those is me, so that's 27 students. That kind of worries me. Oh, yeah, we're up to 28 students now. Woohoo! So anyways, last time we worked on basically the simple harmonic oscillator. Today we're going to jump into not only finishing chapter 14, but we're going to jump into chapter 15 a little bit, which is more about waves, which is the next logical conclusion or stepping stone, if you will, from a simple harmonic motion. Waves, simple harmonic motion is basically a repeat in time, whereas waves are a repeat in space and time. So you not only have some phenomena that repeats itself in time, but you also have some phenomena also repeating itself, that same phenomena, in fact, in a different point in space. So you have, for instance, the peak of a wave at x equals 1 meter, and then a little while later it reaches x equals 2 meters, and a little while later x equals 3 meters, so on and so forth. But if you plot that versus time, you have the same thing going on. So it's a more robust version of simple harmonic motion. So we're going to study that, and I'm going to talk more about the physics of it. The math and the problem solving is pretty straightforward. I also created some video. Well, I started creating some videos for applying the initial conditions for the differential equation that is a simple harmonic oscillator. But I've had some problems getting them posted, so they'll be posted probably before Monday, but that'll give you ample opportunity to see, hey, what if this is the initial condition where the initial position is the actual amplitude, but the initial velocity is 0? Well, what about if the initial velocity is the max velocity and the initial position is 0? And then finally, what about something in between? So I did 3 initial condition problems that are actually intimately related. And those will be videos that I'll post on my YouTube page. And if you'll notice, I also updated my list of YouTube videos in the useful documents link at the top of your Canvas page. But I will post it here as well. When I do those extra problems, I will post them in this week's module, maybe even next week's as well. So let's go ahead and get started. Anybody have any questions before we do get started? Okay, so I'm going to start by sharing my screen so we can see the math problems that, the physical problems that we're actually trying to solve. So we've already talked about a mass on a spring. That was the simple harmonic oscillator problem. I even showed you how to add a dampening force. So instead of just being m d2x over dt squared is equal to negative kx, you would also have another term that would be negative b dx dt, because it's they're using the air resistance force or fluid resistance force that's proportional to velocity. There's another one that's proportional to velocity squared, but then when you do that, you get into what's not no longer considered ordinary differential equations. It's actually sort of a nonlinear differential equation. It's ugly, and because of that, we don't want to solve it. So we're not going to. That being said, once you learn mathematical techniques to use, for instance, computer software, computer programming to solve differential equations. All the differential equations are just about pretty straightforward. The project that I was working on when I was trying to get my PhD at Chapel Hill was something called the Grand Challenge, and the daughter of the Grand Challenge, and the son of the Grand Challenge, and the grandchild of the Grand Challenge. But that was just solving a huge, nasty system of nonlinear partial differential equations that are linked to each other. But even then, that was just something we could do. Is just needed brute force. Someone has a question. I'm checking right now. Okay, gotcha. Yeah, that's for the end of class. No problem. So solving differential equations really isn't that big of a deal in the real world. Obviously, there's some that are not easily solved, and there's some that are remaining not solved. But finding closed solutions like we're getting here, where it's just a sign of this with some particular number, that's the rarity in differential equations. Differential equations are among the most difficult things to solve if you're actually looking for closed solutions like sine or cosine or hyperbolic sine, or even the more special things like Laguerre polynomials, Hermite polynomials, spherical harmonics, Bessel functions. All those different things are very special solutions that are just a nightmare even to work with the functions by themselves. But it's amazing that they happen to find these very specific differential equations that apply to reality, and whose solution is, for instance, a Bessel function, or a Bessel function. Actually, should be pronouncing that Bessel, but the vacuum cleaner company's got me in problems. So, anyways, let's look at one more example of how to deal with a mass on a spring, and that's problem 1 here. And it really this one sort of brings to home everything that you need to understand about the physics of oscillatory motion. That includes wave mechanics, not just mass on a spring. It includes mass on a spring, it includes a pendulum, it includes a kid on a swing set, and it includes waves. So in this problem, we have a mass of 275 grams. So I'm going to write M equals 0.275 kilograms. It's suspended from a spring and the spring stretches 11.5 centimeters. So I'm going to write X is 0.115 meters. And the spring is then turned horizontally and attached to a wall over a nearly frictionless surface with the same mass attached to it. So we're taking and hanging a mass on a spring to basically allow us to determine the spring constant. And then we're going to take that same mass with that same spring and set it up horizontally, so that same spring can now slide back and forth on that frictionless surface. If the mass is pushed toward the wall, compressing the spring till it is 8 centimeters. So I'm going to write X initial is equal to 0.0800 meters. From the spring's equilibrium point, determine the following. So notice they are pressing that, and it's sort of implied here that they're then going to let it go. So the velocity initial must be equal to 0. So V initial, I'm going to write as 0.00 meters per second. That's another piece of data that allows me, since this is a second order differential equation, I need 2 initial conditions. That allows me my second initial condition. And in part A, I want to know what is the frequency of oscillation in both radians per second. So I want to know omega, and in hertz. So I also want to know F. Part B, I want to know the position of the mass as a function of time. So that's X of t. In part C, I want to know the velocity as a function of time. That's V of t. And part D, I want to know the acceleration as a function of time. That's A of t. And then, yeah, A of t. I got confused because I said A of t and I was thinking D, and all of a sudden everything went to kapooey. All right, so E, define the relevant terms in each of those functions, which I'll just leave E as a blank because I'll understand what that means later. And then finally, what is the position of the velocity? The position and the velocity at t equals 0.300 seconds. So that's part F. I want to know X of 0.300 seconds. And I want to know V of 0.300 seconds. Yes, I'm writing a lot of stuff right now, but I'm just recording that so we can turn over the document cam. So I've got all the important information. Now I'm going to stop sharing the screen, show you my document cam, and you'll see what I have written down. So notice here, I wrote down the mass that's suspended from the spring initially, but it's also the one that oscillates on the spring horizontally. I wrote down the initial stretch of the spring when it was hanged. Notice I did use proper grammar there. Hanged vertically. And then I showed the x initial, which is the compression of the spring, which I'm going to call the positive x direction, by the way, of 0.0800 meters. And the initial velocity, which was implied to be 0. And then I asked what's going on there. Okay, so those are really the problems that we're trying to solve here. And I was able to prepare well enough to work these out in advance. So hopefully I've got all the arithmetic down pat and didn't make any careless mathematical errors, but there's always a chance, you know. So what we're going to use for part A is that F is equal to K times X, which gives us, in fact, that K is equal to F over X, but K is not mass. That's a common mistake people make. They'll just take 0.275 and divide it by that. That's not a force, so that's not going to get us. So I need 0.275 kilograms times 9.80 meters per second, which I'm going to write as meters per second squared. I'm going to divide that by 0.115 meters. And from that, I will get a K value, which, by the way, they didn't ask for, of 23.43 newtons per meter. Okay, they did not ask for that at all, but I need that for some subsequent calculations. I did carry one extra digit there, which is good practice. In fact, most of these calculations I actually did earlier, and I left all the digits on there. But I kept recording at least one digit. So you might find a slight difference with your digits and mine, but that's due to me carrying all the digits, okay? The minimum should be carry one digit and see what happens. So in some sense, you would be in maybe even more right than me. Now that I have that, I can actually calculate part A, which is omega is equal to the square root of K over M, and that'll come out in radians per second. So that's the square root of 23.43 newtons per meter over 0.275 kilograms. If you'll notice, a newton is a kilogram meter per second squared. So when I divide a kilogram by that, or into that, then that gets rid of the kilogram, and I get meters per second squared divided by meters. So that's just per second squared, which means nothing per second once you take the square root. So that's a radian per second, and I get 9.231 radians per second. And that's omega.
Could you bring it a little closer?
Yeah, so that's called the angular frequency, or the frequency in radians per second. So if you got your calculator, for instance, in radian mode, you would want to take that and multiply it times the time in seconds, and that would give you the output of the trig function. Most of us run it the other way around, so I'm frequently taking this, multiplying it by time, and then converting it to degrees so I can use the rest of it. Now, what they also want is the frequency, but we know omega is equal to 2 pi times the frequency, because remember, the frequency is the number of cycles per second, and basically the number of cycles is 2 pi radians. So you actually have to multiply by that. That gives me that F is actually equal to omega over 2 pi, which I take 9.231 and divide it by 2 pi. And when I did that, I got a frequency of 1.469, carrying again one extra digit. And that comes out in cycles per second, which is called a hertz. Okay, so those are both answers to part A. Any questions on that? Pretty trivial, right? Part B, they want to know what is x of t, and this is really what you're supposed to be doing, guys. I have given you the solution for the differential equation. You need not go through the details. I mean, you should do it once to make sure you can understand it and use it ad nauseum, just to confirm that it is in fact the solution. But I've given you the solution so that you may use it over and over again. So the solution for this is x of t is equal to a cosine omega t plus phi. And when you actually plug this into that second order differential equation, there's a very specific requirement for the omega, and that is that omega is equal to the square root of k over m. Now, the phi and the alpha are something that comes from the initial conditions. So I need to, in order to write the x of t as b wants, I really need to make use of the initial conditions. So the initial conditions are x of 0 is equal to, I'm again calling this compression, this pushing against the spring, I'm calling that the positive x direction. So in doing that, I'm going to say this initial position is 0.0800 meters. A lot of people would actually call that a negative displacement, in which case you'd call that negative, and then your graph would be upside down compared to mine. I'm really not liking how blurry that looks. Let's try my other pen. Yeah, that looks a little more crisp. Okay. So that's x of 0. I also am going to take v of 0 is equal to 0.00 meters per second. And we know that v of t, which is dx over dt, is negative omega a sine omega t plus phi. Okay. So when I actually apply this condition in here, I get 0.0800 meters is equal to a cosine of phi, because the t is 0, so that omega t disappears. And then when I do it with this one, I get 0.00 meters per second is equal to a negative omega a sine of phi. This is equation 1, say. This is equation 2. Just like I did before, I'm going to take 2 and divide it by 1. This is not always the best way, but it almost always works. So why not stick with it? When I divide equation 2 by 1, I get 0 divided by 0.08 with units anyway, or without the units anyways, is equal to negative omega is 9.231 radians per second times a over a, and then the times a would be sine phi times cosine phi down here. You can see basically everything's canceling out. I get a 0 on the left, so all this stuff multiplied, which the a's cancel out, by the way, but I get negative omega tangent theta is equal to 0. So I'm going to choose. There's a buttload of tangents that give me 0. Remember, the graph of the tangent function is basically this. It comes up at 0 and hits that. That's at pi over 2 and negative pi over 2. But then there's another one over here. And then another one over here. So there's a bunch of different values of phi, say, or angles that could give me 0. There's one there, there's one there. I'm going to choose arbitrarily that one. Okay, so I'm going to choose phi is equal to 0, and that's actually going to make life for me a little easier. So finally, I can now write that x of t is equal to, once we now know that phi is 0, equation 1 becomes a times the cosine of 0, which is 1. So a is equal to 0.08 times cosine of, and I'm going to include the actual numbers, 9.231 radians per second times the time. So that's the position as a function of time. The velocity as a function of time, on the other hand, is negative omega times a. So I've actually got to make the 9.231 times 0.08, when I actually do that math, and I've done it already, I get negative 0.7385 meters per second. Now you can see I'm actually working into part C at this point, times the sine of 9.231 radians per second times time. So now I've figured out part B, that the position as a function of time is that. This also says that A, which equals X max, is equal to 0.08 centimeters, or 0.08 meters, sorry. Okay. And that's actually with 2 other decimal places on the end. Now, when I do this, what I'm actually pointing at is actually part E. So I should really label it accordingly, but I'm trying to point out in real time what the relevant parameters are. You can see that this number here is just A, and that is in fact the amplitude of the oscillation, which is X max, which is 0.0800 meters. Tried to write that a little neater so people can see it. You can also see from this that V max, which is really, we're talking about part C now, because part C wanted to know the velocity. So I'll put a C here, underline that, or box that off. And then part E of this would tell me, oh, V max, which equals omega A, is actually equal to 0.7385 meters per second. Again, I'm keeping 1 extra digit there. So now I've actually answered part of E as well, because in E, they just want to know really the relevant parameters. Okay. So does everybody see how I did X of T and V of T?
Could you just like bring it closer?
Yes.
It's pretty blurry on our side.
So I will sort of show it this way so everybody can see all the work and then see the final result. This makes me ill that it's blurry. Let me show a little bit of everything here. Okay. Again, remember, these are all in my Google Docs document. I've been keeping up with that too, so you shouldn't have any problem downloading those. I usually take the picture right after class and usually post it within the same day, so that works out. Let's work on now part C, which is part D, which is actually the acceleration as a function of time. So D, I want to know A of T, which is actually equal to dV dt. Of course, we see that dV dt, or that V is negative omega A sine. So when I take the derivative of this with respect to time, I get a negative of the derivative of sine, which becomes cosine, and then multiply it times omega. So I ultimately get negative omega squared A cosine omega t, like that. Again, the phi we already eliminated, so it's exactly omega t. So I can actually write out, once I take this velocity that I had. Go ahead, somebody said something. Okay, since I had that velocity right there, omega A, all I have to do to get the maximum acceleration is multiply this times omega. So I'm going to multiply that 0.7385 meters per second. I'm going to multiply that by the 9.231. So you can see I'm really going to get on the order of meters per second for the actual acceleration. So ultimately I can write A of T is equal to negative, when I multiply again that 0.7385 times 9.231, I get 6.817, carrying 1 extra digit. And that is in units of meters per second, which I'm going to write for ease, meters per second squared. And that is times, in this case, it's going to be the actual, did I actually write the right number down? Hold on. Yes, I did write the right number down. And that's going to be times the cosine of 9.231 radians again per second times time. I'm being really pedantic about putting this radians in there. There's two things about that. One, I want you to know that's what it is, so it keeps you straight in terms of whether you're using the degree mode or the radian mode with your calculator. But two, I also want you to remember that radian is technically just a pure number, so you can drop it and add it almost whenever you want to. So now I've gotten part C, or excuse me, part D, which is the acceleration as a function of time. I can also add that to that part E and say that A max, which equals omega squared A, is actually equal to 6.817 meters per second. And this is a part E result as well. Okay. Now, the other thing that I would really like to have just as a real physical parameter is the period. And remember, the period T is equal to 1 over F. We already calculated that F, so I'm going to say the T is really 1 divided by 1.469 hertz, and that'll come out in seconds per cycle, which is really just seconds. So I'm going to go ahead and include that as one of our key parameters, and that is 0.6806 seconds. So this also is an answer to part E. It's a characteristic of the actual oscillatory motion, and that's going to come in handy when I go to do the very last part of the problem, which is where I'm trying, or actually the next to the last part of the problem, which is where I'm trying to relate the phases. And that's what part E was about, is tell me about how these curves are related to one another, what's the phases about, and that sort of thing. So let me take off for a second and write up what part E is. So the best way to look at this, and you can do this, for instance, in your labs when we do oscillatory motion, I'm going to try to put all of these graphs on the same line. So this would be T, and this would be X of T, and this right here would be the amplitude. Whoa, Nelly. I see that you are not seeing what I'm writing because I'm writing it so low down there. So I'm going to put that down there. I'm also going to say that this is like a quarter of the period. This is a half of the period. This is 3/4 of the period. This is a whole period. I'll put a dot over it so I don't forget. Then another quarter, then another half, then another 3/4, then another period, roughly. Okay. Now I'll come down here and say this line right here is another t-axis, but this t is, of course, for the velocity, and the max velocity is omega A. And then finally, I'll put a final t-axis down here, and this is for the acceleration, and that is omega squared A is the max. Okay. So we can see from our function x of t that this is just a straight up cosine. So what a cosine graph is going to look like would be basically it starts high, goes to 0, reaches its minimum value, which I actually went down a little too far there, reaches its minimum value there, goes to 0 again and reaches that there. And of course, then that repeats itself like this. God, I could have made that. I don't think I could have made that any uglier than I did. Anyways, I forgot that I was that I'd made everything in quarters, so that didn't turn out as well as I'd like it to. Maybe I'll fix that later and pretend it never happened. Okay, so that's the actual position as a function of time for this oscillatory motion. Okay, that's not that big a deal to analyze at this point. The bigger thing is when you start to take it and compare it to velocity. Well, velocity is the negative of the sign. So the velocity being the negative of the sign means it should go like this, 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 like that. So what you see is the actual amplitude is a maximum when the acceleration is 0. Okay. That's just like when you're on a swing set. When you're on a swing set, your position swinging is at its max height at exactly the instant that your velocity is 0. Right? Because if it had any more positive velocity that way, it would go higher. If it had any a negative velocity going this way, in other words, it would have come from higher up. So that's perfectly reasonable. And it also tells us that when the potential energy for the mass on a spring, right, when the potential energy of the mass on the spring is a maximum, the kinetic energy is in fact 0. And now we can see finally that the acceleration, which is just a negative of cosine. Now, in that case, a negative of the cosine is going to start here and go there, and then there, and then there, and then there. And this period, by the way, remember I took the time to figure that out. This period right here is 0.6806 seconds. And this is 2 times the period right here. Okay, so this is the period along this line, 0.6806 seconds, and this is 2 times the period. Now this continues on this way, looking like that, looking like that, looking like this, and then finally looking like that. And now you can see when the actual velocity, let's say, is a maximum in the negative direction, the acceleration is actually 0. And that's also consistent with a swing set, though it's hard to see a swing set combining with a spring. But once we do a pendulum, you'll see the exact same thing happens. But as you're swinging in a swing set, you are at the peak height. And as you fall lower and lower and lower, you speed up, speed up, speed up, speed up. But once you get to the lowest, you have no ability to speed up anymore. There's no more kinetic energy to be gained from a decrease in potential energy because you are at your lowest point. So in fact, the fastest point on the swing set is when you actually have 0, if you want to say, you actually have 0 amplitude. So that's kind of neat. You can also see that the maximum acceleration, say here and here, actually occurs when the velocity is in fact at its maximum. Okay, so the maximum acceleration starts to occur when the velocity is at a maximum. So anyways, that's really the analysis that you should think about and see how you're going from, in this case, a maximum potential energy with zero kinetic energy. And then at 0 kinetic energy, you actually have, or excuse me, at the maximum kinetic energy, you actually have 0 potential energy. And the force, in fact, is 0 when you have 0 potential energy. Okay. So hopefully that helps you. Now, finally, in part F, and this relates to something we're going to do a little bit later. So in part F, they would. Someone have a question?
Yes, I was saying, can you move that back up some a little bit?
Yes. In part F, they're wanting to know what is what is x of t at 0.300 seconds, and what is v of t at 0.300 seconds. If you actually go ahead and take the time, now you got to be careful because you're going to use this function right here. But if you put in 9.231 and multiply that by 0.3, that's in radians, and therefore your calculator will need to be in radians, or you need to convert this radians to degrees by multiplying by 180 and then dividing by pi. That's actually what I did, was calculated it as 9.231 times 0.3, and then I multiplied that number by 180 and divided by by pi, and then I took the cosine of that. When I actually did that, I got the x position is in fact negative 0.9315 meters. And when I did the same thing for velocity, I got negative 0.2686 meters per second. Okay, so these are actually my answers to part F, and I should look and see if they make any sense with respect to the graph. Remember, the period is 0.6, so if you go about halfway of that, in fact, a little bit further than half, because, or excuse me, a little bit less than half, because half would be 0.34. So halfway to here would be right here. I need to go a little less. And when I do that, I see the velocity is in fact negative, and I see the position is in fact negative. And the position should be, whoa. I think I left a 0 out of here. This should be 0.09 as opposed, no, that can't even be 0.09. Notice this number. Anybody see a problem with this number? The velocity doesn't seem to be a problem to me because the velocity is 0.7385, but the maximum position should be 0.08. So I'm wondering if I multiplied it by 8 as opposed to 0.08. So let me check this real quick while we're here. Now you see why I work it ahead of time. So what I did was 9.231. That's in radians per second times 0.3. Now I multiply that by 180. And now I divide that by pi. That gives me 4.897 times 10 to the negative third. So 0.004897. So I'm saying in this case, 0.9231 radians per second times 0.300 seconds is equal to 0.004897 degrees. Okay, but that also happened to be 2.769 3 radians. Okay, so can anybody confirm that those numbers are right for me?
Wait, you did 0.91, no, 9231 times 0.3?
Yes, 9.231 times 0.3. And I should have gotten 2.7693.
Yeah.
Okay, y'all confirm that. Cool. Okay, and then can you confirm when you multiply it by 180 and divide by pi, you get 0.004897?
I got 15.867.
Okay, that's a lot different now, isn't it? Oh, are you in radian mode?
I'm in degree.
Okay, and you did you took the cosine of, or actually, that was just your conversion to degrees, right?
So I did 0.9231 times 0.3 in degree mode. I'm still in degree mode.
Right.
And I got 0.27693. Multiplied it by 180, which gave me 49.847.
Oh, okay, I see my calculator. Whoa, that's weird. I ended up dividing. Whoa, what the heck was I doing there? I ended up dividing by 180 like some crackhead. So let's first off just say what I want to write this down again just to make sure. So we're going to say 9.231.
9 point or 0.9?
No, it's 9.231 was the actual angular frequency. Can anybody confirm that part? Because that could be a problem. That should have been the square root of K over M. K was 23.43 and M was 0.275. So that should have been on the order of 230 divided by 2, or 130. Square root of 130 should be around 9. So that, yeah, that seems right to me. Times 0.3. And I get 2.7693. 2.7693 radians is what I got for that. and 2.7693 radians times pi, or excuse me, times 180 degrees per pi radians should give me, so I'm going to say times 180. I'm going to say divided by 3.14159. Ooh, yeah, I got 158. That's much better. I remember doing that before. I got 158.67.
I did too.
Okay, that's cool. Thanks. And that's degrees. Okay, so now I've got to take the cosine of that and multiply it by 0.8, and we'll check this answer then. So I'm going to take cosine of that 158.6693, and that gives me 0.931. I'm going to multiply that by 0.08, and that gives me 0.07452. And it actually should give me a negative, by the way. So this is the actual right answer. This one's a
It's very
no.
blurry.
Sorry. So this is the actual right answer, negative 0.0452. Now I have to double check that for the velocity one to make sure I didn't make a screw up there. So let me check the velocity one. I'm going to take, in this case, it's actually the sine of that same number, which is the 158.669. And now I got 0.36374 for the sine. And now I'm going to multiply that by my Vmax, which is 0.7385. So that gives me a velocity of 0.2682686. Yeah, that's exactly right. So this one's fine. So let me just rewrite it since it's turned out kind of ugly. I'm going to say x of 0.300 seconds turns out to be negative 0.07452. And actually the way that worked out was it was 4.51974. Just to give you extra digits in case there's any confusion. Meters, and then I've got V of 0.300 seconds was negative 0.268 meters per second. And that one turned out to be 268.6292. So that really is carrying all the extra digits, giving you all the details that you may or may not want. Okay. I'll bring this up so everybody can see it. So hopefully that helps everybody understand how to apply these equations in general. Now, in addition to that, we need to know in general what types of expressions can we use. Are we always going to be stuck with X, V, and A, or is there some other way to analyze this that might even be a little easier? And it turns out there is. What I'm going to do is now imagine the scenario where we start to analyze this energetically. So we just talk about the actual energy of the problem. Now I worked all this out as a pre-derivation, but I think it might be better just to work it as a physics problem instead of a separate derivation. But by doing so, we'll end up going through the derivation anyways. So that brings me to share my screen for number 2, which hopefully that's the right one. Yeah, that looks like it. Okay, so number 2, what is the total energy of the harmonic oscillator in the problem above? So I'm going to write it out generically first, just write out the solution for any general case. We know that x of t is equal to a cosine omega t plus phi, and that v of t is actually equal to negative omega a sine omega t plus phi, so that the total energy E is equal to 1/2 k times x of t squared plus 1/2 m v of t squared. Now, okay, hold on a second. I'm writing down this stuff, but I wanted to make sure. Okay, and then they're ultimately asking for the velocity. So you see A is they want to know the total energy, B is what's the kinetic energy, C is what's the potential energy, D is what's the velocity. So I'm going to show you that you get the same result that we got in the previous part. And then what are the energies and positions if the amplitude is 1/2 of the, or excuse me, if the X is 1/2 of the amplitude. So I'm going to stop sharing, turn it back to my document cam. So this energy, there's a total amount of energy, and that's fixed. That turns out to be a constant. I'm going to show you basically what that constant is. I suspect you might even be able to guess what it is now. Can anybody tell me in terms of, let's say, A, what the total energy should be in terms of that A?
Would it be like 1/2 k a cosine omega t phi squared plus 1/2 m times negative omega a
Yes.
omega t and all
Yes, that's
such?
exactly right. And if you choose to eliminate sort of everything but the K and the K and the M, excuse me, the K and the A, then you'll get through sine squared plus cosine squared equals 1, you'll get 1/2 KA squared. If you instead choose to eliminate everything but M and omega A, then you can ultimately see that it'll be 1/2 m times omega a squared, which is really just a total 1/2 mv squared, where v is omega a, the v max. So yeah, E total is actually equal to 1/2 k a squared, or you can say it's equal to 1/2 m v max squared. But when you do that, you got to remember V max squared would be omega squared A squared. So either one of those is acceptable for the side, but it does show that it's constant. Now, in this case, they're asking for the kinetic energy and all that good stuff. I can say, for instance, in part A, the potential energy U is equal to 1/2 k x of t squared. So that's 1/2 times k times a cosine omega t plus phi. All this will be squared. So I'll put that in hard brackets. That gives me, in fact, 1/2 k a squared cosine squared omega t plus phi. Of course, it was referring to that previous problem, but that previous problem just had phi equals 0 and a equal to 0.08 and k equal to 23.43. So we can put all these numbers in all day long, and we'll get an easy enough result. And in fact, what I'm going to find out is that when I multiply k, the 23.43, newtons per meter, and a, the 0.0800 meters, then I ultimately get U is equal to, you can check this math yourself, but it's basically 0.0749913. I'm carrying a lot of extra digits here. Joules times the cosine squared of 9.231 radians per second times t. So that's part A. Hopefully I'm remembering which one they asked for first. I think I asked for potential energy first. Now part B, they're asking for the kinetic energy. The kinetic energy is basically the 1/2 mv squared. So K is equal to 1/2 mv of t squared. Well, that's 1/2 m, but then v of t is negative omega a sine omega t plus phi. Put that in square brackets, squared. So I get 1/2 m omega squared a squared sine squared omega t plus phi, like that. So in our particular problem, the phi is 0, the omega is 9.231, and it turns out if you multiply the 0.275, the omega, which is 9.231, and the A, which is 0.0800, lo and behold, you get 0.0749913 joules times sine squared of 9.231 radians per second times time. So that turns out to be your answer to B, the kinetic energy. And obviously, if you add these two, you're basically going to get this number, and you can factor out cosine squared plus sine squared. So the total energy E is just 0.07499913 joules, again, carrying 3 extra digits because it's sine squared plus cosine squared, which is just 1. Does that make sense?
Can you bring it a little closer, please?
Yes. So I worked this out generically for any, cosine omega t plus phi, but then I actually used the results that I had in the previous problem to fill those in. I didn't actually show you me filling those in. I just pointed little arrows to where those numbers go, and y'all can verify for yourself what it is. But you do see it's about 0.0749, so roughly 75 thousandths of a joule. Any questions on that part? Now, part C, they really wanted to know what the kinetic energy and what the potential energy, and then what the kinetic energy is when the position is at 1/2 the amplitude. Before that, I want to point out something that you can get by using this energy being equal to 1/2 kx squared plus 1/2 mv squared, and using either this or this. You can get a couple other expressions that I'm just going to give you. You can derive them yourself. I derived them. It's really not that big a deal. But basically what you will get is V as a function of time is equal to plus or minus the square root of K over M times A squared minus X squared for any particular X. So if you want to know X, or I should really call this V of X instead of V of T, then this is the way you can compute it. Obviously, you have to make some judgment decisions on your own because of that plus or minus there. You have to decide what part of the period it's in to decide whether the sign should be positive or negative, but it can actually give you the value. Now, also, if you take and factor out K A squared over M, that actually will show you basically, remember the square root of K over M is actually omega. So you can actually use that, factoring out all that stuff, and get that it's actually equal to plus or minus V max times the square root of 1 minus x over a squared. Because remember, this is actually omega squared, and it's under the square root, so I just get omega. If I factor out a squared, that'd become a squared times parentheses 1 minus x over a quantity squared. So when I have omega times basically a, we know omega a is from this part, V max is equal to omega a. So that's why I can actually say V max is that. Okay, so those are really nice expressions you can use when necessary. It's not unlike the expression we use when we're doing elliptical orbits in terms of gravity. We can take the total energy equal to this, and then we can use that to solve for, say, the velocity at any point in time or something like that. So it's just that kind of thing that can help you. So that's one of the things I would have on my equation sheet if I was you, for instance. All right, so the last part, which was part C, is where they wanted to know U at 1/2 A. Well, I think you can already tell what it should be, because U at 1/2 A, basically E is equal to 1/2 K A squared. So the potential energy would be 1/2 K parentheses around the A over 2, and then square it. So I should really get 1/4 of the energy, and that's really what the result is. But just to brute force calculate it out, it's 1/2 times 23.43 newtons per meter times 1/2 of A, which is 0.0400 meters. That'll be squared. Lo and behold, when you do that math, you get 0.01874 joules, which is in fact equal to 1/4 of the total energy. Okay, if you take that 0.0749913 and divide it by 4, you'll get that figure. Similarly, the kinetic energy at 1/2 A should just be the total energy minus U at 1/2 A. So I think you can see that's going to have to be 3/4 E. But again, let's do the brute force method. So it's 0.0749916, or was it 13? Excuse me, 13 joules minus 0.01874 joules. And in this case, you end up getting 0.05625 joules, which is in fact equal to 3/4 E. It's okay, Hercules. You're just having a bad dream, buddy. My dog's having a nightmare, which is kind of ironic because yesterday I looked out, or my neighbor looked out in my backyard, and there was like a turkey buzzard sitting on my shed, just waiting for Hercules to come out. He had like a 5-foot wingspan, and of course my dog's Hercules is less than 5 pounds, so he'd be a nice little snake, tasty morsel for a turkey buzzard like that. And I think that might have been what the guy was planning. So it's okay, buddy. You're just having a bad dream. All right. So any questions about that? So see how you can use energy methods too. It's really nice, and it's pretty straightforward. And a lot of times it's a lot easier to use energy methods. So what I wanted to go to now is consider a couple different cases that are kind of odd. I will do this via a problem. So the physical pendulum and the torsion pendulum are about the same thing as the regular pendulum. So let me first start off with a little intro to the regular pendulum. Boy, we only have 12 minutes left. This is not helpful. With a regular pendulum, what you'd have is basically an axle for it to rotate. You have a very, very low mass rod or string, and then you'd have a relatively large mass compared to that spring. So it's not really that this has to be that light. This could weigh 100 pounds if you wanted to, as long as this weighed like 10, 20, or 100 times 100 pounds. It would be fine. And you'd say that's an angle theta. Well, when you use the summation of the torques is equal to I times alpha for this, you see that the force applied to this is mg, and it acts along that way. This is a wonderful opportunity for you guys to see that torque can equal lever arm, the component of the lever arm perpendicular to the force, or the lever arm times the force, component of force that's perpendicular. In this case, I will finish this vector upward and make a right triangle out of that. And by doing that, I see this angle is theta. And this is, in fact, the component of the lever arm perpendicular to the force. And I think you can see that that is, in fact, L times the sine of theta. So I can now say that this torque, which actually is causing a decrease in theta, that torque should be negative mgl sine theta. And that, of course, is equal to the moment of inertia, which for this simple case is just mr squared or ml squared times d2 theta over dt squared. Now, if I were to do a blob of matter, and this particular location was the center of gravity, then that L would point to the center of gravity, and this I would be whatever the moment of inertia of that blob of matter is. So it turns out to be the same differential equation. It's just the L, instead of going to the center of mass, it actually goes to the center of mass of the blob, or the center of mass of, or the center of gravity of the blob. Okay. So this ultimately becomes d2 theta over dt squared plus let's say m g L over I theta, or excuse me, let's do sine theta, is equal to 0. I hate what just happened there. My OCD is getting the best of me. So the sine of theta. Now, this is a beast. This is a very complicated differential equation to solve. But luckily, we don't have to, because we can make an approximation. We can say for small theta, sine theta, which equals theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial. This is something you should do. You should do your Maclaurin series for sine theta, for cosine theta, and for e to the x power. All three of those are related. And when you do that, I think you will find something very valuable. But you can see when theta is small, then theta cubed is really small compared to theta. And then dividing it by 6 is really smaller. So you can really just say, okay, well, d2 theta over dt squared plus mgl over I theta is equal to 0. Now we have our simple differential equation where theta is equal to some theta 0. Well, actually, I'll just say theta is equal to some theta 0 times cosine omega t plus phi. Now I'm jumping ahead of myself. That doesn't have to be the theta 0. That could just be any kind of amplitude, but in most cases it does turn out to be theta 0. Now, in order for that to be the case, then omega has got to be the square root of mgl over I, which for this problem is the square root of mgl over ml squared, which just becomes the square root of g over L. Okay, so that's really wonderful for a pendulum. Omega for a pendulum is equal to the square root of g over L, which means the period t, which is 2 pi over omega, is equal to 2 pi times the square root of L over g. And of course, the frequency is 1 over that, so on and so forth. If you're doing a complex pendulum, then it goes back to this formula. And you can actually use that to solve problems about, for instance, if you want to find the moment of inertia of an object, you can just find its period of oscillation about a particular point. So let me quickly, since I only got about 6 minutes left, let me share the screen here. We've done number 2. Number 3 is right here. And they're saying, what is the frequency? They want to know F equals question mark for a period, for a pendulum that has a period of that has a length of 1.000 meters, and G is equal to 9.80 meters per second. And then in part B, they want to know what is that same period and frequency. And in this case, at the top of Mount Everest, where G is equal to 9.773 meters per second, all we have to do is period is equal to 2 pi times the square root of L over G, which equals 2 pi times the square root of 1.000 meters over 9.80 meters per second. When I do that math, someone could back me up on this. 1 divided by 9.8, take the square root of that, multiply it by 2 pi, and I get 2.007 seconds is the period. Okay, that's carrying 1 extra digit. That's part A. The frequency is 1 over that. So 1 over 2 is essentially a half. So we're going to call it 0.4982 hertz. So that's part A. Part B, if we wish to do this for Mount Everest, then we get basically 2 times 3.14159 times the square root of 1 divided by 9.773. In this case, I get 2.00985. 986, say, and I'm actually carrying 2 extra digits here, and that's seconds, which means the frequency is equal to 1 over that. So 1 divided by second function answer is 0.49755 hertz. So yeah, you could actually use this to determine the acceleration due to gravity, for instance. Let me stop sharing for a second so you can see the actual work I did. All I did was 2 pi times the square root of L over G is the period. When I did that for 1 meter and 9.8, I got 2.007. So if I can measure time to the nearest thousandth of a second, then I should be able to discern the difference between G at Mount Everest and G at sea level. And these are the results I got. That's also, like I said, in the other example, the other problem that you see right here, they can do, you can use that to figure out the moment of inertia of any object. So if you had a moment of inertia of a meter stick that you wanted to know, Then all you have to do is find the center of mass, which you can do by just balancing it. You find the center of mass is at the 50 centimeter mark, duh. And then you find out its mass, and then you find out its period of oscillation. And for this, you say T is equal to 2 pi times the square root. Now, in this case, it's we found was mg mgl over I was the omega. So period would be I over mgl. So it'd be 2 pi times I over mgl. So all I really have to do for this, I had T is equal to 1.45 seconds. I had L is equal to 0.500 meters. And I had M is equal to 0. That's supposed to be kilograms, by the way, 0.980 kilograms, not grams. So I'll stop sharing. And you can see all I got to do is square both sides. I get T squared is equal to 4 pi squared I over mgl. So I is actually equal to mgl T squared over 4 pi squared. And that's pretty straightforward to calculate. 0.980 times 9.80 times L of 0.500 times 1.45 seconds squared over 4 pi squared. And that would actually give you the moment of inertia. It looks like I've run out of time. So next time we'll have to spend time on chapter 15. And then the following time we'll spend on chapter 43. So I'm going to write next chapter 15. Then chapter 43, which is elementary particles. So in case I got the number wrong, I'm pretty confident it's chapter 43, but that's what we're going to cover a little bit maybe the next time, but definitely the time after that, which would be our last day of class. Our final exam will be the following Tuesday. Somebody might want to take it on Thursday, so I'll make 2 versions. But remember, you have to have your respondus available. You need your respondus lockdown browser to work. You need your respondus monitor to work. If that doesn't work, you need to set up an appointment at the testing center and take it there because I can't. You have to actually be monitored for this final, and this final counts basically as much as the midterm. But here's my great prize to you guys. If you score higher on the final than you do on the midterm, I will substitute your final grade for it no matter what. But I will not do the opposite, okay? So if you make lower on the final, that's what you get to keep, okay? But anyways, you guys are done here. You're free to go. This should help you get through at least chapters 14 and 15. I don't think the questions I asked for 43 are too terribly hard. So you might even start doing that. The practice test is up. Have a good weekend. Stay safe, and stick around if you have any questions. I'll wait for the last person to leave.
Have a good one.
Professor Younger.
Yes, sir. You too.
You said when was the exam?
It'll be a week from Tuesday. Which, that's the 22, so 23, 24, 25, 26, 27. It'll be a week from the 27th, which 30 days has September, April, June. So it'll be 30, 27, 28, 29, 30 be Thursday. 1, 2, 3.
So somewhere
4,
in like
5.
the 1st of May?
It's like the 5th of May, yeah, if I remember correctly.
Okay.
Yeah, 4th of May. Sorry about that. So yeah, the 4th of May is your final exam. Let me write that down here. May the 4th be with you.
Professor Younger.
Yes.
I know you talked about the homework stuff, like the
Mhm.
late stuff on that earlier in the class. I just want to make sure that I already also sent you an email and just want to check if you were fixing it like after the class.
Yeah, they should be fixed now. Look at it and see if they haven't been. But I did it late last night, like maybe even 1 a.m.
Got you.
So check and see if it's fixed. If it's not, send me another email and I'll check your grade specifically, Peter.
All right, thank you.
No problem.
Yeah, I also had a concern about the homework because when I went in, it said 11:59 a.m. and then I seen at the top that it said no credit for late work. So I waited until the class to bring it up to you because I wasn't sure if you're gonna respond to
Okay.
email. I'm sorry.
Peter Lee and Jasmine Grant.
But yeah,
I'm writing down the
definitely
names.
okay. I'm definitely gonna get on it whenever you change it.
Okay. Yeah, it basically what happens is I go in and I give it credit for turning in late. It's supposed to be 5% off per day, up to a maximum of like 35%. So when I changed that, it was supposed to redo all the grades. Have you checked it since early this morning, or is it or have you actually looked at it today?
I'm looking at it right now.
Yeah.
Okay, and it's still not corrected. Which homework set are you talking about specifically that's giving you that currently you're having problems with?
It should have been the chapter 11 conceptual is what was due yesterday.
Okay, all right, I'll check that one specifically for you, and hopefully I'll get it all straight. But I will check that. Remember, you do have a final coming up, and all those. There might even be a test out right now, so make sure you don't miss your test date, that sort of thing.
Okay.
All right, have a good one.
Thank you, you too.
Yeah, Mr. Younger, I completed mine yesterday at noon,
Okay.
but it's still saying a 0 out of 27.
Yeah, that's weird. It should be doing better than that. All right, yeah, let me check that out. Who was this that was just talking? It wasn't Rosa, that was Andy.
Yes, sir.
Okay, I will check that one as well.
Professor Younger, I'm on the same page as these
Oh,
other
you are?
guys.
And you're having the same problem?
Yeah, I completed it yesterday, just a little bit past noon, and it's still saying no grade.
All right, let me check this out, and I'll get back with y'all. I'll send y'all an email to everyone instead of individual people, just to let y'all know what's going on when I find out something. Okay.
All right, thank you.
No problem. Anyone else have any questions?
Have a good one, Professor.
You too. Yeah, Jason, you have a question for me? You can chat it if your mic's not working. Okay, I see what you're asking, Jason. I just saw your chat. Okay, let me look into that. So we're talking test 5/test 6, and this is Jason Tickle. All right, I wrote your stuff down, Jason. Let me find out what's going on with that, and I will send you an email as well. I see that you said you sent me some screenshots, so that'll be helpful. Anything else you had, Jason? Gotcha. Yeah, I'll check that out for you, Jason. Anybody else have any questions?
Yeah, Professor, I actually had a question.
Go for it, Brett.
This was just from some of the emails I had sent you a while back. I had thought I had turned in for test 4, and I actually had not.
Okay.
And I just wanted to confirm with you whether or not that was something that I could actually be able to actually submit or not.
Well, let me, yes, I will let you do that. Let me go right there right now before I forget. Brett, Michael,
Yep.
Micah, something like that. Okay. Now I'm trying to see where I'm at in the course. And you said it was test 4?
Yeah, I just had, I don't know what had happened. I had pretty surely turned it in, but yeah, it ended up getting locked. So as long as I can do it, that's fine. And I appreciate you opening it up.
No problem. Wait here so I can make sure it's going to work for you,
Okay.
if you don't mind.
Yeah, that's fine.
I think I just opened someone else's out too, but that might have been my 242 class. Who knows? I think I did. Yeah, that was my 242 class. Dang it! Why am I keep getting in stupid Zoom instead of my actual Canvas course? It's aggravating me. Ah, there's my Canvas course. Stupid. Okay, 241. Here I am. Nope, I didn't want that. I wanted that. Okay, working on it. So that's that. Test 4. Here we go. Ooh, okay. Hey, stop it. This thing just randomly moves. It's not nerve-wracking at all. Okay, so I'm going to attempt to do what's called moderate the test, which I think allows me to open it back up for you that asked for or made the request. And I'm going to do that, and I want you to see if it actually works.
Gotcha.
So JKM. Yep, it said you did not do that. And manually unlock the quiz for the next attempt. It might only give you one attempt. If it does, send me an email and I'll open it up for 2 more attempts.
Okay. Thank you very much. I appreciate it a lot.
No problem. Let me know either way whether it opens up for just one or what, even if you don't want to take more than one.
Okay, that's fine.
All right. Thanks, man.
All right. Thank you. Bye.
Bye-bye. Anyone else? Vanessa, Richard, or is it Ricard? Anyone? Oh, I love what you've done with your hair, Vanessa. Those glasses really accent your tongue. Come on, that's funny stuff. I think someone's mic doesn't work. All right, well, I'm going to let you guys go. It seems like no one's here. You have a great weekend, and email me if you need anything, and I'm going to go work on your mastering to see if something funny was that. Have a good day.